So today we are going to look at stoichiometry problems. Right, with stoichiometry, it's basically all about looking at the quantitative values of how much or the amount of reactant used to form the specific amount of product. Okay, so basically, it's like looking at baking something. We have cupcakes just because of stoichiometry and the fact that it exists. So with stoichiometry, if we looked at cupcakes, we would see that, oh, we may need 2 eggs to form 12 cupcakes. Just because we have 2 eggs doesn't mean we only get 2 cupcakes. And so stoichiometry is all about getting a certain amount and reacting it to get a certain amount of product. And so normally you will be given some type of word equation. And so with word equations, you are going to have to pick out what you know and sometimes form the formula depending on what you are looking at. So let's pull out our unit sheet and our notes and review the different steps that we have in order for you guys to really understand the concept of what's going on here. So just give me 1 minute. So when I'm looking at your notes, stoichiometry, like I said, is the quantitative relationships between amounts of reactants and the amounts of products formed by the chemical reaction. So we're going back and looking at our mole conversions and building off of this. So remember, we start with grams and then we use the periodic table's formula mass added up per 1 mole to get 2 moles. Okay, and so we are also reviewing chemical equations, remembering that we have our reactants, we have our products, and then we look at the ratios after we have balanced it. So I have a 1:3 to 2:3 ratio, which basically means that for every 1 mole of ethanol, it reacts with 3 moles of oxygen to produce 2 moles of carbon dioxide and 3 moles of water. And so I think we can all agree that oxygen and water are not the same thing. Carbon dioxide and oxygen are not the same thing. Okay, and if it was the same thing, we would have a very strange life. Oxygen is what we breathe in, it helps us live. Carbon dioxide is what we breathe out. And if we only breathe in CO2, then that means that we would die. So of course, we are understanding that these compounds are not the same thing, but we have to figure out how much carbon dioxide would form if I had so much of oxygen, if it wasn't just a 1:1 ratio. So first off, we have to build that relationship, that quantitative relationship, by looking at the mole ratio. Okay, and so the mole ratio is basically like a fraction, comparing how everything's related using the coefficient ratios. And remember, the coefficient represents the number of moles of a compound, whereas the subscript is the number of atoms of an element within that compound. So looking at these relationships, I can see that I have 1 mole of ethanol, which is 1 mole of C2H5OH, is equivalent to maybe 3 moles of oxygen. And so that's the ratio, that's how they overall relate in a problem. Okay, so with this in mind, you can form vice versa or opposite relationships. So 3 moles is also equivalent to 1 mole of ethanol. Okay? And so with this, we can continue on looking at the relationships. Okay, so I just looked at ethanol and oxygen. Now I can look at ethanol and CO2. So 1 mole of C2H5OH is equivalent to 2 moles of CO2. And vice versa. 2 moles of CO2 is equivalent to 1 mole of C2H5OH. And so it's kind of like when I tell you to look at all the mole ratios, you FOIL out. Ethanol, oxygen, ethanol, CO2, ethanol, H2O. So 1 mole of ethanol is equivalent to 3 moles of H2O. And vice versa. 3 moles of H2O is equivalent to 1 mole of C2H5OH. Right, now we have to look at the other relationships. So now oxygen and CO2, oxygen and H2O. So I have 3 moles of oxygen for every 2 moles of CO2. And of course we do vice versa, or the opposite, depending on what we are trying to cancel out. Doing 3 moles of oxygen for every 3 moles of water. And just because it's the same number does not mean that we can simplify yet. It will simplify when you plug it into the calculator later, but we want to show how these things actually relate. Okay. And the last thing is we want to compare CO2, so 2 moles of CO2 for every 3 moles of H2O, and vice versa. And so when we have 2 reactants and 2 products, you should have a total of 12 mole ratios. And any of these mole ratios can be used in our stoichiometry problem to help relate compounds to other compounds. We can't just change oxygen into water. We have to show how the relationship forms. So that being said, now we can work with stoichiometry problems. When we are finding the mass of a reactant and product using stoichiometry, we first have to form the reaction and balance it. Second, we convert to moles of whatever they gave us if necessary. So sometimes they may give it to us in moles already, so we don't have to convert to moles. Next, we are going to set up the mole ratio, so set up the relationship between whatever compounds you're looking at. And then we're going to use that mole ratio to calculate the moles of our desired substituent. And substituent is basically our desired compound or element that we're looking at. And lastly, we are going to convert 2 moles to the desired unit if necessary. So there is an example in your notes, but I am going to go ahead and move to your unit sheet so that way we can get some practice problems going. So first off, with stoichiometry, we are going to look at just mass to mass and mass to mole problems. So let's look at number 1. Number 1 says, if 240 grams of sodium carbonate react with magnesium hydroxide, how many grams of sodium hydroxide are formed? Okay, so the first thing you're going to want to do is you're going to want to write your reaction on your paper. I have sodium carbonate reacting with magnesium hydroxide to form our sodium hydroxide and magnesium carbonate. And so this one is already balanced for you. We'll work up to you balancing and writing your equations again on your own. Next, we go back and read it. It says 240 grams of sodium carbonate. So that's right here. And I always write what I'm working with underneath so I know where to start and where to end. And then it says how many grams of sodium hydroxide. So this is sodium hydroxide. I put a question under it and I put grams. So I know I'm working from part A to part B. So now that I have the first step of balancing the equation out of the way, I go to step 2, converting to moles. So I have 240 grams of sodium carbonate, and I convert to moles, and you guys know how to convert to moles by now. Okay, so I want 1 mole of sodium carbonate, and be sure to write the elements underneath it because we need to know what we're canceling out and what we're going to. So 1 mole of sodium carbonate equals 105.99 grams of sodium carbonate from the periodic table. And it's always a good idea to add your formula masses somewhere on your paper so I can see what you're working with, and you can always get partial credit if for some reason you don't add it up or plug it into your calculator correctly. So grams of sodium carbonate cancel out, and we're left with moles of sodium carbonate. But I'm still trying to get to grams of sodium hydroxide. So the next step is we find the relationship. Okay, I have 1 mole, because there's nothing right here, 1 mole of sodium carbonate is equivalent to 2 moles of sodium hydroxide. So I'm going here, so I'm going to put moles of sodium hydroxide on top, and I'm going to put that 2 mole at the top, and that comes from the coefficient, and 1 mole of sodium carbonate at the bottom to cancel out what I started with. Now I'm going to convert to my desired unit, which is grams of sodium hydroxide. So I have 40 grams of sodium hydroxide for every 1 mole of sodium hydroxide. and now sodium hydroxide in moles will cancel out, and you are left plugging it into your calculator. This is where that ND button comes in handy, okay? So I hit the ND button, and I have 240 times 1 times 2 times 40 divided by 105.99 times 1 times 1. And so that gives you 181.15 grams. But remember, we have to maintain significant figures. So what they give you in the problem originally, which was 240, that has 2 sig figs, I have to answer my question in 2 significant figures. And so I have 180 grams of sodium hydroxide as my final answer. Okay? So that is a straightforward way to do grams to grams or mass to mass for stoichiometry. Okay? And so each problem is done like this. You just have to make sure you write the chemical reaction and balance it correctly. Alright, so there are several other problems that of course, do not go all the way to grams. I've said that we're going from mass to mass, which is just grams to grams, but there are a few that just go from mass to moles, and those are very simple problems because we're just taking a step out. So I'm going to go ahead and skip some of these examples. Feel free to do all of these to help you get a better understanding of it. Usually, I want to say around 7 here, where I'm taking out the skeletal equation and the balanced equation, and you are forming it yourself. So it's very important that you go back and look on how to do this, okay? But I'm going to skip to one that goes ahead and asks for moles, so that way we know exactly what we're working with here. So if we look at number 5, it says how many moles of table sugar are decomposed to give 500 grams of carbon. Okay, and so I'm going to write down my equation. C12H22O11 yields 12 carbons and 11 waters. So I know I want to know the number of moles for sucrose. So I'm going to put question mark and put moles at the bottom, or you can put X because it's your unknown value. It's what you're working towards. And then 500 grams of carbon. So now we just follow the steps. It's balanced already for you. So the next step is to take grams and convert it to moles. Okay? So I have 12 grams of carbon, and make sure you put the elements so you're not confused on what you're going from to what you're going to. And so grams of carbon will cancel out, and I have 1 mole of carbon on the top. And next we use the mole ratio to bridge the gap to show the relationship between moles of carbon and moles of sucrose. And so I see there's 1 mole of sucrose for every 12 carbons. Okay, so moles of carbon will cancel out. And so then now we go to our desired unit. Well, it's asking for moles, and I'm already in moles, so I don't have to take this a step further. I'm done, and I can just plug it into my calculator. So we are going to hit our ND button and do 500 grams times 1 divided by 12.01 times 12. And we get 3.469. So I'm going to report to 3.47 because I have 3 sig figs because they put a decimal place at the end here. So this is 3.47 moles of sucrose. Okay, and so that is just going from mass to moles. Very simple. We're just taking out a step. All right, so let's go one step further and look at one that doesn't have the skeletal equation written for you and kind of makes you think a little bit harder. All right, so if I was looking at, let's say, what mass of hydrochloric acid is produced when sulfuric acid reacts with 250 grams of 95% pure sodium chloride. All right, so we have to write the skeletal equation. So let me refocus this because it's looking just a tad bit blurry. Oh, made it a little bit worse. All right, so let's take this problem. All right, it says we are reacting sulfuric acid, which is H2SO4. And if you don't remember what sulfuric acid is, always do scratch work. So sulfuric, it used to be 8. So I have sulfate, which is SO4, 2 negative. And then I had hydrogen, which has a +1 oxidation state. So swap and drop, and we get H2SO4. And then it says it reacts with pure sodium chloride. Sodium is +1, chlorine is -1. So swap and drop, and they are equal. So just 1 and 1 as their subscript. So then it says it produces hydrochloric acid, but that's not the only thing it produces. We can't just put this as its product and not include sodium and sulfate because it just would disappear. So let's go ahead and combine sodium and sulfur, or not sulfur, sulfate, excuse me. Sodium has a +1, sulfate has a 2 negative, so swap and drop, and it also produces Na2SO4. So it's very important that you include all the products because when you balance it out, of course, it's going to change the mole ratios. So I have 2 hydrogens here, so I put a 2 here to fix that, 1 sulfate here, and 1 sulfate here. So that fixes that, okay? And so what we're going to do is we're going to also include a 2 here to fix chlorine, which also fixes this 2 here. Okay, so we have a 1 to 2 to 2 to 1 ratio. So now we can actually begin the problem. All right, I have 250 grams of 95% pure sodium chloride. And I want to know what is the mass, which is grams, of hydrochloric acid. So first off, we have to find our true starting number. Okay, so I'm going to scratch out my scratch work right here. It says 95% of sodium chloride, okay? So I'm going to take 95% of 250. So I changed 95% to 0.95, and I'm really working with 237.5 grams of sodium chloride because that is the pure form. 5% is inert, which means that it's not actually part of the reaction. It means that it's like an impurity. So I'm going to start with 237.5 grams of sodium chloride, and I know that I'm going to first convert to moles. So 1 mole of sodium chloride is equivalent to, and I pull out my calculator, and I have 22.99 plus 35.45, which is 58.44 grams of sodium chloride. So grams of sodium chloride will cancel out. Now I want to get rid of moles of sodium chloride. So I put moles of sodium chloride at the bottom, and I go to moles of hydrochloric acid at the top because that's what I want. And so I use my coefficients. I have 2 moles of sodium chloride for every 2 moles of hydrochloric acid. Moles of sodium chloride will cancel out, and now I go to my desired unit, which is grams of hydrochloric acid. And so when we add that up, we are going to get 35.45 plus 1.01, get 36.46 for every 1 mole of hydrochloric acid, and moles of hydrochloric acid will cancel out. So let's hit that ND button and plug it in. 237.5 times 1 times 2 times 36.46 divided by 58.44 times 2. So we get 148.17 grams of HCl. But now we have to go and report to the correct amount of sig figs, and we always go based off of the original number they gave us. So 250 has 2 significant figures, so I run around to 2 significant figures here. 48 is closer to 50, so I have 150 grams of hydrochloric acid as my final answer. Okay, so hopefully that's not too bad. We are just combining our ionic naming and covalent naming with our predicting products along with our balancing equations. So hopefully you can see how chemistry is building on itself. If you are struggling with naming or balancing or predicting products, you need to go back and look at the videos for that. Okay, so now with stoichiometry, we go from mass to mass, so grams to grams. We can go from mass to moles, so grams to moles, and then we can also bring volume into it. And volume is not really different. If anything, it's simpler. So let's look at number 1. How many liters of oxygen are necessary to react with sulfur to prepare 500 liters of SO2? So first we have to form the actual skeletal equation. So I have oxygen reacting with sulfur. So I know oxygen is diatomic, so I have to put a 2 here, plus sulfur, and excuse this wonderful autofocus. Okay, and so then it's going to form SO2. Okay, and so from here we can see that it is balanced already for us, and so we have a 1:1:1 ratio. It's easy. So I have 500 liters of SO2, and it's wanting to know how many liters of oxygen will form. So I put a question mark, put liters under it. So we put what we start with right here, and now we are going to convert using moles. Right? So remember when we talked about moles, if we see something at STP, that means we use the conversion factor 1 mole equals 22.4 liters. And since we're considering all of these at STP, I can use this number to convert from liters to moles. And so remember, moles is what we use to bridge the gap or to create the relationship between oxygen and SO2. So I'm going to put 22.4 liters of SO2 to equal 1 mole of SO2. So liters of SO2 will cancel out, and now I use my mole ratio. I have 1 mole of SO2 for every 1 mole of oxygen. And so moles of SO2 will cancel out, and now I go to my desired unit. I want liters of O2, and so I want to get rid of 1 mole of O2, and I can go back to liters using this 22.4 liters of oxygen. So moles of oxygen cancel out, and we can get our answer. Hopefully you guys see the relationship that these 2 steps cancel out, but we still show it to show how we are converting from one element to the other. Your biggest impact is going to be based off of your mole ratio, so you definitely want to make sure that's right. So we don't even have to plug this into our calculator. Okay, we know this cancels out, and our mole to mole ratio is 1 and 1, so that's going to give us 500 liters of oxygen. So once again, volume to volume is very simple. All right, let's continue to look at some other problems that we may see. Okay, so I can look at, say, number 5. What volume of oxygen is necessary to completely burn 12.5 moles of methane gas? So let's write this equation first. We have CH4 plus 2 oxygens, and it yields just 1 CO2 and 2 H2O molecules. Okay, always go and check to make sure it's balanced. 1 and 1 carbon, 4 hydrogens, 4 oxygens, and 4 oxygen. So it's balanced. And so with this, it's saying what volume of oxygen, so I'm going to put a question mark and put liters under oxygen, is necessary to completely burn 12.5 moles of methane gas. And we know this is methane gas because this is CO2, this is water, so that is our last option if you don't remember what methane gas is. So I am going to put my starting point right here, and it's already balanced, so we've completed step 1. Step 2 is to convert to moles if necessary, and it's not necessary because I'm already at moles. So the third step is to find your mole ratio, so this is 1:2 ratio, and use it to go to your desired substituent. So my desired substituent is moles of oxygen, so I'm going to put 2 moles of oxygen on top, and I'm going to put my 1 mole of methane on the bottom. Moles of methane are going to cancel out, and so now I go to my desired unit. Well, my desired unit is liters of oxygen, and so I know it's at STP, so I can use 1 mole of oxygen is equivalent to 22.4 liters of oxygen. So moles of oxygen canceled out, and so now we just plug it into our calculator. I have 12.5 times 2 times 22.4 divided by 1 and we get 560 liters of oxygen. And I'm just going to put a decimal place right here to make that zero significant. We don't do this always, but I'm going to do this right now so that way we don't have to change into scientific notation or do anything crazy right now. Okay? So hopefully you feel good about volume to volume or moles to volume. Basically, if you follow these 6 steps, it doesn't matter if you're going from mass to mass or moles to mass or vice versa, or going from liters to liters, grams to liters. We have a connection using what we know about the mole, so mole equaling something on the periodic table, 1 mole equal 22.4 liters, and using the mole ratio to convert to one compound to the next to see how these specific amounts of reactants and products come together. And using stoichiometry and using these conversions, we will then look at percent yield, and we will also look at limiting reactants. And of course, for our advanced chemistry students, we will look at excess reactants. So definitely look for those videos posted and use this unit sheet. You can pause this video now, look at part D, do some of these examples, or if you are struggling with mass to mass, use part A as your examples, and of course come see me and I will show you the answers for these.